restarting the whole class. So what would be the direction for the air resistance? Air resistance will always be aimed in the opposite direction of instantaneous velocity of the object at that instant. So we cannot very specifically say for an overall duration of movement what would be the general direction of air resistance. It would be a changing direction for throughout the motion. But if we want to divide it into two different components, we can go ahead and try to do that. For example, let's say this is a surface where we are shooting a projectile from here at some angle in this direction, and that projectile is having a motion like that. If we now have two different individual velocity components, let's say this was u, so let's say this is our ux and this is our uy. These are the two component of the initial velocity. Because ux is such a quantity which will remain unchanged. To remain unchanged, I'm saying when air resistance is considered 0, but whenever air resistance is there, ux will be affected. So, and horizontal motion is not changing direction, but vertical motion will change direction. The vertical velocity component of the initial velocity will remain upwards up to the maximum point, and then it will become downwards. So the air resistance in the horizontal motion, which is actually a force, will be related. So let me just write, how can I write related? I'm not going to write proportional because it's not actually proportional. Let's say I'm going to write this direction to represent that this is related. This is related to only horizontal values magnitude, because in this case horizontal component will not change direction. So if it is more, you have more air resistance. If it is less, if you have less air resistance, so on and so forth. So I'm using this sign because there might be some square, cube, there might be some other variables involved over here. There is Stokes law, which is also another law from fluid dynamics. You don't have that. I'm just saying you for the sake of conversation that, so for the direction of air resistance, for the horizontal component of air resistance, we don't have to bother for direction. As for the vertical component, I mean, once we have defined this as a vertical component, this velocity. Let me write with a different color maybe. Let's say this is the vertical component labeled with red. So if you consider different position, you're going to have different values of air resistance of upward velocity, and then you're going to have increasing value downwards over here, and it will have the same value like this for the same symmetric point on the right side. So for this part of the motion, till it reaches horizontal, till the particle reaches the maximum point, we can say the vertical component of air resistance will be aimed downwards, and for this segment of the motion, we can say the vertical component of air resistance will be working upwards. So that much we can say for the sake of direction, but instantaneous direction will be always against the velocity. Does that answer your question, Hassan?
Yes, sir.
Achha. Okay, so let's go into the concept for momentum. What do we mean by that? So we'll starting the topic momentum in today's class. Momentum is a pretty interesting.
Was this all the previous classes recap?
Momentum की last से पढ़ाई थी तो on देखे?
No, sir. Momentum and आगे, sir.
No, this was a question of Hassan's answer. Hassan asked us a question that what would be the direction for the air resistance when the object is moving? He also included beyond the maximum position. So I said that the generic direction for air resistance cannot be defined overall for the overall motion, because air resistance always works in the exact opposite direction of instantaneous velocity. So I just gave the answer of a question.
Okay, sir.
Sure. So momentum is a physical quantity that is expressed. The sign that we use for momentum for a typical case is small p, and it is expressed as the product of mass and velocity of an object. Important term, this is represented as velocity. So just to represent that this is a vector quantity, I might as well give a bar sign over here to represent this is a vector quantity. So momentum will also be vector quantity. The theoretical definition is very simple. What is momentum? Momentum is the product of mass and velocity of an object. To be honest, momentum is defined by this very simple equation and in this very simple manner for very preliminary or primitive level Newtonian mechanics. If you slowly go higher up in the level of physics expressions, the definition for momentum can change a lot. So there is a certain video which almost reaches the point of a meme that I shared once in my Facebook timeline about the momentum. I still have that video saved. If any of you want, I might actually share you the YouTube link later on, or might as well put the description of that video in my in the description box for when I upload this video. So for your level, this is the definition of momentum. You have to understand momentum is a vector quantity which has the same direction as the velocity of the object. Now, important term is that what do we mean? What does this term momentum physically mean? I mean, what is momentum? How should we perceive? It's a product of two different quantities, good. But what does it actually physically mean? Momentum of an object is pretty much a measure of an object's inertia. Inertia is a term that we use. It's not actually a measured quantity, but it's a very important concept whenever we are talking about motion of objects. The term inertia is very much important for the understanding that inertia of an object is the resistance that an object represents against change of velocity. So if you have an object that is undergoing some sort of motion, if you want to change the velocity of that object, the object would show some obstruction or resistance towards that change. Object would not appreciate the change of its current velocity situation to a new velocity situation. Might as well be in terms of magnitude, in terms of direction, or maybe both. How much of that resistance does an object show is practically a measure of that object's inertia. It's not actually measured with any SI quantity. It's just a physical concept. So objects which are difficult to accelerate in this case can mean speed up, slow down, or turn, either of them or both or all, or alternately combination of those. So that's what we mean by inertia. Now let me give you a simple example. If you have a really big lorry, let's say a long vehicle, container carrying lorry, which has let's say 16 wheels or something like that. So it's a pretty massive object. If it is moving at only a speed of 5 kilometers per hour, which is not a very high speed, 5 kilometers per hour is pretty small. That object would be very difficult, or let's say impossible, to be stopped by a single person, because the mass is so big. So whenever you multiply, you get a pretty high inertia. That's one example where we don't have too much mass, too much velocity, but because the mass is too big, it has a significant momentum. Then again, if you consider the bullet that is shot from a gun, the slug of the bullet, I mean, what do I mean by the slug? Okay, any bullet is defined by basically two parts. One is the chamber, where we have the explosive of the bullet, and then there is a solid metal object which is supposed to shoot itself from the shell because of the explosion. So usually the shell is pushed out of the gun after every shot is done, and the solid metal object that shoots itself out. So usually we call this thing the slug. This thing can have different properties and geometry, whatever. I'm not getting into that discussion. So whenever we shoot a certain bullet, let's say this slug, which comes out as the projectile out of a gun, this might be of very small mass. This might as well be, let's say, 50 gram. 50 gram even is also quite high, let's say 30 gram or something like that. So the mass of a bullet is not that big, but one single bullet is pretty much difficult for a single person to stop by their physical strength. I mean, unless getting shot at. I mean, if it penetrates a person, that's basically not stopping. Why am I saying now? Why is that? Because a bullet doesn't have that much mass, but it has very high velocity. So the product of these two things causes it to have a very high momentum. So momentum is basically a measure of inertia, that how much force might it require to have any significant acceleration from the initial velocity to new final velocity that we want to provide to the object. So that's a primary concept for momentum. Momentum is a pretty interesting concept, and when Isaac Newton gave the 3 laws of force in his book Principia de Mathematica, he actually used the term momentum to explain the rule number 2, which we didn't teach you in your O-levels, because in your O-levels the concept momentum was not included. However, it has been introduced to the new class 9 batch from this year, so which is a good thing. I got to teach them the idea of momentum in the very last class, so it's pretty much the same class, no big deal. So what Isaac Newton said in his before I give you the before I go into the description for the second law of motion, let me just give you a simple scenario. Let's say we have an object of mass m, which is moving towards right with initial velocity of u. At t equals to 0, let's say this is the incident when it is at t equals to 0. So this is happening. So at t equals to 0, we're gonna apply a resultant force on the object. Let's say we're going to apply a force of F on the object. I'm using the term resultant, but I'm not showing the resultant sign over here. I'll bring up the resultant sign later on. Just for the sake of easier writing, I'm doing this. So we're gonna apply a force over here, and we're gonna keep pushing this object over a duration of, let's say, t amount of time. So within this duration, this is the object is gonna reach from here to here. So let's say this is the new position of the object. Let me draw that with black maybe. So why am I not drawing a good circle? What is this? Okay, good. So let's say this is the new position of the object where the amount of time that has passed by is, let's say, that is t. So t equals to t, it means t amount of time has passed. And over this entire duration, we kept on applying this F force. F force was continuously being applied on the object on this entire journey. And let's say after t time, it has a final velocity of v, which will be definitely bigger than the initial velocity. And the mass is pretty much the same. So we can write that the initial momentum of the object was mu, and the final momentum of the object is mv. What Isaac Newton told us in his second law of motion, so second law of motion, he told us the rate of change of momentum on any object is directly proportional to the force applied onto it. So he said it like this: the rate of change of momentum. So change of momentum divided by time. This is basically rate of change of momentum. This is directly proportional to force. So that's what he said. Now we're going to work further with this proportionality and eventually see what comes out of it. So just to convert this thing into an equation, we can give a proportionality constant. So delta p over time equals to constant k into f, and then we can break down this whole thing. This would be given by final momentum minus initial momentum divided by time equals to k into f, which gives us mv minus mu divided by time equals to kf, which gives us m multiplied by v minus u divided by t. What I'm doing is I'm taking the m as common out, so and writing the v minus u divided by t as a single expression for obvious reasons, because I want to replace this thing by acceleration. So ultimately I get mass into acceleration equals to that constant k into f. So this is the equation that we reach up to. Till that point of time, the unit of force was not a defined quantity. Isaac Newton was the first person who defined the unit of force, and that's why we called it Newton. Maybe he named it, or maybe someone else did it, I don't know. But the unit of force is defined as Newton. So the unit of force, which is, let's say, 1 Newton, was defined from this equation in such a way that this constant k, it becomes 1. Now, how does that mean? This was the definition that was given for 1 Newton force. It was said that the amount of force, listen to me carefully, the amount of force that produces 1 meter per second square acceleration when applied on an object of 1 kg. So I actually started from the right and went on to the towards left. So the amount of force that produces 1 meter per second square acceleration on a 1 kg object is 1 Newton, which means if you have a 1 kg object and by applying a certain amount of force, you produce exactly 1 meter per second square acceleration on the object, the amount of force that you're applying on the object is defined as 1 Newton. So if we replace all of these values over here, so this is 1 Newton, this is 1 kg, maybe black, this is 1 kg, and this is 1 meter per second squared. What we're going to end up with, we're going to get, for numerical values, we're going to get 1 into 1 equals to k into 1. Ultimately, the value of this constant k is becoming 1, which makes the whole equation much too simpler. ultimately, because the because this k value becomes 1, this equation can be rewritten as F equals to ma. That's the equational expression of Newton's second law, which you came to learn in your O levels. But it was actually derived from this set of equation, and this was the actual proportionality relationship that Isaac Newton gave us in his book, the second law, that rate of change of momentum is directly proportional to resultant force applied on the object. This is one thing which you have to understand, and it will come useful later on. You already know this equation. You have used this equation a lot in your O levels mathematics. So and you have to understand this F actually represents resultant force, not a single force. I use a single force because for this scenario, I assume that this mass was only subjected to exclusively this force over here, not for a lot of different forces, or maybe even if a lot of forces are involved, this force was resultant. So I can also write, just for the sake of completeness, that resultant force was applied over here, and I could also write the resultant sign over here. Doesn't make much of a difference for my setup here, because F was the only force, which also happens to be the resultant force. One interesting thing that we should take on is this one. Have a look at this expression. Delta P over T equals to K into F. We define the equation in such a way that K becomes 1. So what does this equation become? This equation becomes this. Delta P over T is equal to F. This happens to be the new defining equation for you kids for force. Now you might wonder, what does it even mean? New defining equation. How does the definition of something can change? Definition of something can change. Definition of something can become more deeper. Definition of something can become more vivid. Definition of something can become inclusive of new variables. So if you are asked that what is force, for a qualitative definition, you might write it is a push or pull on any object, which is not untrue, but writing that would not score you any mark for your S level. The examiners want more. If you write it is the product of mass and acceleration of an object, there is a 50-50 chance that you might score the mark, you might not score the mark, because this is also considered to be O-level stuff, which is not untrue. It is not incorrect. What is expected out of you in your AS level is that you write this definition. What is force? Force is the rate of change of momentum of an object. This is the new definition that you should aspire to. Try to remember this thing and try to write this equation. If you wonder why do you have to bother to even know new equations, because we are going to use this expression a lot for our purposes. The other thing that we actually get from this equation is what is called impulse. If we just cross multiply this equation, we can write delta P equals to force into time. This expression, force into time, is also called impulse on an object. Now, what do I mean by that? Impulse is basically the product of force and time on an object. So if you apply, let's say, 100 Newton force on an object for 2 seconds, the amount of impulse you are providing to that object is 200 Newton second, which is exactly equal to 200 kg meter per second. Amount of impulse is exactly equal to the amount of change of momentum for any object. We define impulse as a new term because this was defined by the early era. Impulse is more commonly used for cases where we apply a large amount of force over a short duration of time. For example, a golf club hitting a golf ball. The duration of collision is actually very small, but the amount of force that works on the golf ball to shoot it to a really high far away distance is actually quite large. So because of that, we use those are the cases where the force is very large but exists for a pretty small time. And you can also use the term impulse for road accident. You can also use the term for the example of meteor collision. For example, let's say there is a meteor that is about to hit Earth's surface. I hope it doesn't happen, but let's say it happens. Then those kind of collisions can be considered impulse. So these are the new terms that we have to be acquainted. Before I get into Newton's third law, using the term of using the concept of momentum, any questions so far?
Sir, impulse tar ekbar bujhaite parben.
Impulse is basically the product of force and time for which the force works on an object. So F into T, this expression, I mean, impulse is actually showed up by this part of the equation. Impulse equals to force applied on an object multiplied by the time for which the force applies on the object. This numerically is very much equal to the change of momentum of the object. If you just change the unit, you get the same value. So what I said, that if you have 200 Newton second momentum impulse applied on an object, then the momentum change of the object will also be 200 kg meter per second. You have to see that where does the kg meter per second come from? It comes from here. This is the quantity momentum. So the unit of momentum should be what? Kg meter per second. So that's the unit for momentum. One thing that I should warn you is that you should not confuse two terms, momentum and moment. They are not the same thing, not even close. I'll repeat, do not confuse the two terms, momentum and moment. Momentum is something that is related to mass and velocity of an object, can be used to give an estimate for the inertia of an object. Whereas moment is the turning effect of a force. Force multiplied by perpendicular distance is what moment is. Okay, হ্যাঁ হাসান বলো।
স্যার ইম্পালসকে একটা জিনিস বলা যায় স্যার, যদি আমরা একটা ফোর্স একটা ডিরেকশনে একটা টাইম পিরিয়ডের জন্য দিই, তার মানে তো ফোর্সের যে ভেক্টরটা ইট ইজ ইনক্রিজিং ইন লেন্থ।
Yes, the total amount of force that we're applying is becoming bigger. Yes.
জি স্যার, ওইভাবে বলা যায় না স্যার যে ভেক্টরটা ফোর্সের ভেক্টরটা বড় হচ্ছে উইথ টাইম?
Yeah, you can say that. You can say that. I mean, if you want to visualize that thing, we can actually do that. We can actually do that. For example, let's say, okay, it's a very good visualization. Well done. Let's say okay, let me put it this way. Let's say you want to hit a golf ball with the club to reach one distance. Let's say there is a person who can also throw a golf ball while holding in their hand over the same amount of distance. Now, if you think about the duration of time for which the ball actually accelerates to get the same initial velocity to reach up to the same distance, those two are not same. When the golf club hits the golf ball, the collision duration is very small. Two really solid objects are colliding with each other. But if you consider a regular human being moving the golf ball in a certain direction, they are going to actually squeeze up their muscle, actually move the golf ball over a certain long distance above their shoulder. So that's the amount of time that they're going to take to shoot the ball. So you can have a different amount of force applied on different amount of time. But if you can make the same amount of momentum change for the golf ball from zero stationary state, you can say that the amount of impulse provided is basically same. So that can be assumed as a longer force vector, because we are basically multiplying the force with a time. Time is a scalar quantity. So that's actually applicable. Yes.
জি স্যার, বুঝছি
Sir,
হ্যাঁ বলো।
so for impulse, do you always consider the contact duration?
Yes, you can say it's the contact duration. Pretty much correct, because for the examples that I'm talking over here, I'm talking about for contact forces. For both the examples, I talked about contact forces. Golf club hitting the golf ball, person holding the ball in their hand and shooting the ball. So there is actual physical contact with the throwing mechanism and with the golf ball. So we can say that is the contact duration. But for many cases, it might be contactless. For example, let's say here is the sun and here is a comet which is trying to go this way, but it cannot go this way because sun is pulling it. So it's gonna bend like that, maybe get a pretty close turn and eventually go out. That happens. That's what comets do. Now, sun is applying a significant amount of force on the comet's mass over a significant large amount of duration. So the amount of momentum change you are having, let's say from here up to here, the amount of momentum change that that the sun's force is causing onto the comet, that can be also calculated by the force multiplied over time. But in this case, the force is going to be continuously changing. So it would be a good idea if we do integration, because the force would be weak when the distance is too large. As the comet comes closer, the force becomes stronger. The force becomes even stronger. At this point, the force will be the strongest, and then as the comet goes farther away, the force will also become weaker. But this is for a very, very large scale scenario where the force can be variable over the duration. To be honest, for even small scale scenario also, the force will actually vary. If you consider a collision, the force of collision between two objects actually never remains at a single value. It gradually increases to a maximum value and then gradually decreases to zero, because objects behave elastically. So that's what happens. So yeah, you can say that it is actually তোমার কোশ্চেনে জানো কি ছিল?
Yes, sir. The contact duration.
Yeah, it doesn't have to be the contact duration. The idea of impulse can be also applied for contactless scenarios, as long as you can do the product of force and time for a certain process. Good. Any further question? Anyone? Okay. The next thing that we're going to see, which is going to involve our momentum discussion, is Newton's third law. Now you might wonder, what is happening? Why do we have to relearn these laws? We don't have to really relearn these laws. I'm just going to give you a very quick recap for Newton's third law, and then we're going to simply jump into the momentum calculation, which leads from Newton's third law. Newton's third law tells us one thing. The basic description for Newton's third law is very simple. It says that every action has an equal and opposite reaction. That's basically it. Within this definition, we have two properties of the forces involved mentioned, that the magnitude of the two forces involved for Newton's third law pair, the magnitude will be exactly equal, and the direction of the two forces should be exactly opposite. This is okay. This is perfectly all right, but there are few more other very important characteristics of Newton's third law, which we have to know and understand. I'm going to write down those characteristics one by one. Okay, might as well write them. The first characteristic is very simple. They have the same magnitude, so the forces have the same magnitude. Other than writing in sign, I might as well write the forces of equal magnitude. So I'm going to write equal. হ্যাঁ বলো
স্যার ওই -f2 এর এখানে মডুলাস হবে না স্যার?
না, এই কোশ্চেনে মডুলাস হবে না, এখানে বরং আমি ভেক্টর দিতে পারি।
ও আচ্ছা স্যার। তো স্যার আমাদের এক্সামে যদি এরকম লিখি ভেক্টরস, তাহলে তো উপরে একটা ড্যাশ মার্ক দিতে হবে, তাই না, সাইনটা?
If you want to mean it to be vector, you can, but তোমাদের O levels is actually O levels syllabus is important na, but ASS syllabus, if you start practicing that from this point onwards, it will be a very good addition to your arsenal of writing and expressing physics terms.
Better বুঝা যায়,
better বুঝা যায় and better express করা যায়. The examiners also get to understand that you really know your shit, which is commendable. By all means, it's commendable. If you don't mess it up, then it's perfectly commendable and highly encouraged.
Yes, sir.
আমি যখন পড়াবো, whenever I usually go through my lectures, I always try to represent the vector equations with vector quantities by giving the bar signs on top of them. But in many of your textbooks, you might not actually see that, which is perfectly all right, because CA people actually, they consider a certain level of difficulty that is universally applicable for everyone, whereas I personally feel slightly different, that whenever I'm trying to give a student concept, it's better to give them the whole picture, at least as much as that concept essentially encompensates. So যতটুকু আছে ভিতরে অতটুকু স্টুডেন্টদেরকে মিনিমাম বলা উচিত। এখন এর মধ্যে স্টুডেন্টরা কতটুকু অ্যাকচুয়ালি মনে রাখতে পারবে বা কতটুকু মনে রাখতে পারা দরকার, এইটা আমরা ওভার দ্য টাইম প্র্যাকটিস করিয়ে, স্টুডেন্টদের সাথে ডিসকাশন করিয়ে, রিপিটেশন করিয়ে, রিভিশন ক্লাস নিয়ে আমরা স্টুডেন্টদেরকে এনেবল করলাম। দ্যাটস ওকে, বাট giving them a fraction of an information or not representing them a full thing, I don't really feel good about that. So that's the shortcoming of mine. Anyway, I think I made my point. বুঝছো কি? তোমার কোশ্চেন আনসার হয়েছে? হ্যাঁ, ঠিক আছে। So these two properties are basically mentioned in the equation, equal and opposite. But the third point that we have to understand, I'm just going to write these properties first. Okay. So what does this line mean? Same line of action. Let me give you a bit of an example. I'm gonna drop some figure over here on this side and try to understand. Let's say we have two different objects. First of all, we're gonna see the linear scenario, and then I'm gonna show you the two-dimensional scenario. I'm gonna look in the syllabus for a while to find out whether you have a three-dimensional scenario in your syllabus or not. I mean, the points that I'm trying to highlight over here is actually not exclusively said in your syllabus, but this is something that I really feel every student should know about Universal Law. Some of you might feel this is redundant, and I would, let's say, for better part of 100%, I'd consider this is redundant, but I consider this very important. A very weird example popped in my head, but I'm not gonna go there. Same line of action. What do we mean by same line of action? Same line of action means that these two forces must be aligned in the same straight line. This is really important, because what is the one thing that you should understand? Whenever we say that two forces are in opposite direction does not essentially mean in the same line of action. Let's say we have a force which is going towards right over here. We have another force which is going exactly towards left over here. They are both aimed in perfectly opposite direction. Their line of actions are perfectly parallel to each other. You have to say that they are in opposite direction. One is going to the right, one is going to the left. But you cannot say they are going in exact opposite direction, or they are not perfectly, because they are not perfectly aligned. For this law, or to be applicable, or cases where this law is applied, these two forces must belong in the exact same straight line. So I was able to show you some example for this thing, and then I moved on to the syllabus content. So let me just show you some example. Let's say we have two bodies. Let me draw with red maybe. So object one is M1 going towards right with an initial velocity of U1. In the same line where another object of mass M2 is going with an initial velocity of U2. So they are moving, they're both moving in the same initial straight line. It's important that we are not messing up with different direction velocity for the time being, but we're going to see that two-dimensional concept after a while. For the time being, we're doing a perfectly linear version of it. So everything is going to happen in a straight line. Forces, velocity, all the vectors are going to maintain one single straight line. That's what we're going to see for the time being. This is what is happening for the M1U1 and M2U2, and then after, so this is before collision. After, and in this case, U1 is bigger than U2, which means this object is approaching this thing faster. To represent that, I try to draw a longer arrow over here, a smaller arrow over here, to represent that this is moving faster. So after a while, they will collide onto each other. Let's say this is the scene of collision. Okay, this is a scene of collision where this is mass 1, this is mass 2. Mass 1 applies a force on the object F2 to the right, and mass 2 applies a force F1 on the object to the left.
Same direction move করতেছে না?
Yes, but when they would collide, this will push onto this object to the right, and because of Newton's third law, this will apply a reaction force on this object to the left. The answer to your question is yes. And let's say this collision that exists between these two objects happens for a duration of time t. Now I cannot actually represent the time t for a drawing like this, so I'm just going to write the variable t over here and might as well give a colorful rectangle around it. So the collision happens for duration of time. This t is very important. It's going to come in handy afterward. That's why I'm including this time t within the figure so that you can have a better visualization.
Sure. Sir, time t is the period of time during which they are in contact, sir. Right, sir?
Precisely. The contact duration is t. Yes. Or I can say the collision duration is t, which is also perfectly the same meaning. Wow. আচ্ছা যেটা অনেক গরম পড়ছে। So let's say after the collision happens, here is our mass 1, which underwent a little bit of deceleration because the applied force is the opposite direction of initial velocity. So now it is moving at a bit smaller velocity than before. So this is our v1, final velocity of object 1, and object m2 will be accelerate a little bit because the applied force was working in the same direction as the initial velocity. So let's say it has a bigger initial velocity, bigger final velocity v2. Still their working line is exactly same. This whole thing is happening in the exact same alignment. This is really, really important. And in this case, v1 is less than v2, which means this is the case of what you call approach. This is the case for approach, and this is the case that we define to be separation. So to hold for just a second. Okay, I'm back. So this is what is happening after the collision, where the final velocity is like this. So this is a scenario that we call the approach case, where the two objects are getting closer. This is during the collision where they're in contact, and this is the case where they're getting separated from each other. This is a case of separation. So before collision, during collision, after collision. So important is that whenever these two objects will collide, these two forces will always work in the same line of action. The next property is these two forces must work on different objects. If multiple forces work on the same body, they are not Newton's third law pair. Newton's third law pair will always work when multiple objects interact with each other. And if you consider two at a time, let's say if we consider the interaction between two objects, and it doesn't have to be that these two forces have to be in contact. For example, the sun is pulling the earth because of gravitation. In the same manner, the earth is also pulling the sun. You might feel that, how does that happen? It happens. That's the whole point of Newton's third law. One thing that I just recently came across in one of the 9gag video, sometimes they put up really good stuff, is that Jupiter has such an enormous mass. It's definitely smaller than the sun's mass, but Jupiter has such an enormous mass that actually the sun and Jupiter practically does not, Jupiter actually does not orbit around the geometric center of the sun. Jupiter rotates around the sun something like this. I forgot the actual name of this. Let's say this is the sun and this is Jupiter, figure not drawn to scale. The center of rotation of these two objects with respect to each other is outside the sun somewhere over here, which is close to sun. So this is the center. So the sun practically orbits around this point in terms of Jupiter, and Jupiter practically orbits around this point. Jupiter doesn't actually orbit around the point that is located inside the sun, because it is so massive. They pull onto each other with really strong force, and because sun is more massive, that center is closer to sun, so sun accelerates less. So that's why it has a smaller radius of movement, whereas Jupiter accelerates more because it has a smaller mass, so it has to undergo bigger amount of acceleration, so it's further away. So why am I telling you this? Is to give you the concept that Newton's third law pair forces will always exist in pairs. They will always exist in pairs. And Newton's third law is one of those laws which is empirically applicable everywhere. I mean, from macro cases like celestial scenarios like the galaxies and the constellations and everything, and also in the very small subatomic cases, even quarks, gluons, they also are subject to Newton's third law. I mean, this interaction is a true interaction as far as I know, without exception, everywhere. So if there are two objects which are interacting with each other, which means that they apply some force onto each other, the magnitude of these two forces should be equal, the direction of these two forces should be exactly opposite to each other, that they should exist on two different bodies, and they should be same type of force, which means that if one is a gravitational force, the other one should be a gravitational force. If one is a contact force, the other one should be a contact force. If one is a resistive force, the other one should also be a resistive force. If one is an electrostatic attraction or repulsion force, the other one should be also electrostatic attraction or repulsion force. If one is magnetic, the other one should also be magnetic. If one is a strong nuclear force, which is a type of one of the four type of natural forces available in the universe, strong nuclear force we call it. So if one of them is a strong nuclear force, the other one should also be a strong nuclear force. So you cannot have different type of forces to be Newton's third law pair. They must exist from the same single phenomenon, like gravitation or friction or attraction between opposite charges or repulsion between similar charges. They must happen from a single interaction and be of same kind of force. These are some inherent properties of Newton's third law that you kids really need to understand. This will come in handy as long as you keep your touch with science. I hope you do that. So from this point, we're going to go further down the line, and we're going to be using this expression. This minus sign is going to be very important for us. The reason we have a minus sign, because we are considering as vector quantities. So we definitely cannot give them to be equal as vector quantities, because they're going to have opposite direction. So what happens now? Let's try to break down this whole equation in terms of momentum. So let's have a look. So F1 equals to minus F2, which means delta P1 divided by T should be equals to minus delta P2 divided by T. এটা কোথেকে আসছে বুঝছো তো? এই জিনিসটাকে আমরা দেখাচ্ছিলাম F equals to delta P over T. So this one is for the first object, this one is for the second object. এখনো পর্যন্ত আমরা ভেক্টর কোয়ান্টিটিতে আছি। আমি ভেক্টর সাইন দিচ্ছি না, কারণ দিলে সবগুলোর উপর দিতে হবে, ওইজন্য আমি আপাতত স্কিপ করতেছি। If I multiply both sides by T, because T is common for both of them, we can simply write this thing as delta P1 equals to minus delta P2. This is also a really important information for us. Whenever two objects will have interaction with each other, the amount of momentum change or the magnitude of momentum change should be exactly equal for both of them, and that should happen in perfectly opposite direction. This is a very important thing. You might say that, well, it's the same thing, forces are equal and opposite basically means the same thing. Yes, it's the same thing, but scientists have used different expressions in different cases to highlight their usage. So this is one of the very important equation. I'm going to talk about this after a while. If we go ahead further to break down this equation, we can write this thing, that delta P1 is basically means what? Change of momentum of the first object, which basically can come in mass of the first object multiplied by change of velocity of the first object, should be equals to minus mass of the second object multiplied by change of velocity for the second object. So I'm writing delta P2. So Delta V1 in this case means the change of velocity for object 1. Delta V2 means the change of velocity for object 2. So how can I rewrite this? Mass 1 multiplied by V1 minus U1. That's the change of velocity for the first object. Have a look at the figure. The initial velocity was U1, the final velocity was V1. So change of velocity of the first object has been V1 minus U1. And the same thing can be written over here for this object 2 minus M2 multiplied by V2 minus U2, which is over here. If we do the multiplication, we're gonna get M1 V1 minus M1 U1 should be equals to minus M2 V2 plus M2 U2. If you do the side changes and arrange it conveniently, we're gonna get this equation M1 U1 plus M2 U2 equals to M1 V1 plus M2 V2. This equation is what we call the conservation of linear momentum. Now, what is that? Have a look on the left hand side of this expression. What do you see? M1 U1 was the initial momentum of object 1, M2 U2 was the initial momentum of object 2. So the sum of this whole thing was the total momentum of colliding objects before collision, which is equals to M1 V1 plus M2 V2. M1 V1 is the final momentum of object 1. Have a look, final momentum of object 1. And M2 V2 is the final momentum of object 2. So this sum is the total momentum of colliding objects after collision. So what are we getting out of this whole thing? What we are seeing that if two objects interact with each other with only their interacting force, which means these two objects in this collision process were only subjected to the action and reaction force that existed between them. So we are not considering the presence of any other third force. And we are considering only two objects are colliding with each other. So we are considering this whole thing as an isolated system. What do we mean by an isolated system? An isolated system is basically a thought of scenario where you try to judge the effect of a very few number of things within a space where there is nothing else. So you segregate that example in a very confined space. I mean, not in terms of volume, in a very what can I say, sacred volume of space in your thought process, where you discard everything else around it. For example, if I'm trying to if I want you to physically visualize this whole process in your head, I want you to think that in the universe there is nothing. You don't even exist, but you have some sense to see. And there are two objects, M1 and M2. There is no other planet. There is no other gravitational force. Nothing. And for some magical reason, they are moving in the same straight line, with the behind object having a higher velocity and the forward object having a lower velocity. That's the visualization that I want you to have. That's what we mean by an isolated system, that they are not affected by any external forces apart from the force that they exert on each other. So F1 is experienced by M1, F2 is experienced by M2, and that these are the only two forces that these two objects are subjected to. Nothing else is there. So for an isolated system where the two objects are the only force applying objects onto each other, this law will always hold true, that the total momentum of the whole system or the total momentum of the colliding objects before collision should be perfectly equal to the total momentum of the collision total momentum of the colliding objects after collision. This is what we call the law of conservation of linear momentum. It's a mouthful, so I'm going to say it again. It's the law of conservation, because both sides are becoming equal. That's basically the idea of conservation. It's called the law of conservation of linear momentum. Now, if you wonder why we are using the term linear momentum, because this whole thing was derived on the concept that the objects are moving in the same straight line. That's why we use the term linear momentum in the statement. We're going to see after a while what happens for a two-dimensional momentum, which it will pop up. But that's the whole point of this thing. if you ever want to write a sentence description of this law, let's say the question says state the law of conservation of linear momentum, you're just going to write this whole thing in sentence. So if I was trying to write this law in sentence, I'm going to write it this way: total momentum of colliding objects before collision is equal to, so I'm going to write this equals to sign as word, this whole thing is equal to this whole thing, and that's the statement of the law of conservation of momentum. এই পর্যন্ত বুঝা গেছে কিনা? I'm going to zoom out, try to put it whole in your.
Sir, isolated system means that, I mean, except the forces we are thought to be considered, none other forces are assumed to be not acting.
Precisely. Gravitational force, no. Air resistance, no. Frictions, no. Nothing else. We just assume those two objects to only exert force onto each other. That's how we want to think about it. But if we want to physically achieve that scenario on an earthly environment, we try to get a situation where the effect of other forces are perfectly same for both of them, or their values are so small that we can practically consider them negligible.
And sir, another question is that the diagrams you drew on top, I mean with the circles, sir, about them, sir, are they always thought that they are moving in the same direction, and after then the collision happens? I mean, I didn't understand how the collision direction would work. Depend on which direction they were initially moving.
In this case, we are assuming that the two objects are going to collide with each other with some amount of force. The force does exist for a certain duration of time. However, the impulse that exists for the two objects, the product of force into time, it is not so big that any of these, let's say the object one is actually reverted backwards. So we are assuming that two objects are still going to move in the same forward direction. That's why we consider all the vector variables over here as positive variable, as positive vectors, except for one, which is f1. I actually wrote f1 equals to minus f2. I should have written f2 equals to minus f1, but you get the point.
Sir, direction f2 হবে না পিছনের দিকে?
Now, I wanted to mention that f1 is the force experienced by object 1. I wanted to keep that numbering coherent. So, I mean, this equation should actually start with this one, that f2 equals to minus f1, because I'm considering towards right as positive for my whole discussion. So this would be a more acceptable starting point.
And sir, one more thing, sir. Over here, we are considering that both objects were actually moving in the same direction, and after the collision of the left object actually moved to the left side, and the right object moved further into the right side, like that.
No.
Okay, sir.
Even after collision, both the objects are still moving in the same direction, but with a changed magnitude of their velocity. So first object be slowed down a little. So I have shown over here that u1 is bigger than u2. So this object is coming fast over here. And what do we have to see? That this f1 was working in the opposite direction of u1, right?
Yeah, yes, sir.
Which means within this time amount of t, object 1 has to decelerate. It is going to slow down a little bit, right?
Yes, sir.
Yes.
That slowed down velocity is over here. So if you want to compare between u1 and v1, I can very much write in terms of magnitude, u1 was definitely bigger than v1 for my example.
And sir, what if the opposite happened? I mean, they were moving in towards each other.
Oh, I'm going to talk about the different directions just after this thing, but any question about up to this derivation, I'm going to get into that question. Hasan.
Sir, একটা question, sir. Time আমরা কেন time of collisionটাকে consider করতেছি instead of the duration of collision of the two particles? Not প্রথমে, sir.
If we don't want to represent the time that is over here, we could also start directly from this point. The reason I'm trying to specify the amount of time so that we can actually convert this equation into this expression. because the time is equal for both of them, we could get rid of the time for both of the sides very easily.
জি স্যার, স্যার আরেকটা কোয়েশ্চেন ছিল স্যার।
বলো।
স্যার দুইটা অবজেক্ট যদি এভাবে মুভ করতে থাকে আর যদি মোমেন্টাম এভাবে চেঞ্জ করতে থাকে তাহলে তো দে উইল হ্যাভ টু ডিফারেন্ট অরবিটালস অফ মুভ, লাইক চেঞ্জ হয়ে যাবে, লাইক ডিরেকশন অফ মোশন ইন দ্য সেম অরবিটাল উইল চেঞ্জ, লাইক একটা ক্লকওয়াইজ আর একটা অ্যান্টি ক্লকওয়াইজ।
I assume you're talking about the spin quantum number.
জি স্যার,
Okay.
লাইক মুভমেন্টটা চেঞ্জ হয়ে যাবে, ইট উইল ইটস এ কমপ্লিট সাইকেল অর আ লুপ।
I honestly do not have a very deep understanding for the spin quantum number, but one thing that I can tell you is we use the term spin plus half or minus half to represent the values, but that spin property is not actually what we visualize to be a physical spin of an object. Electrons having different spin number plus half or minus the half, that has a very deep underlying quantum explanation, because electrons are substances which are so small that they can behave as particle and wave both. So they are, I mean, the spin property is something that is introduced for the sake of completeness of information, but I don't have much grasp about the whole concept of spin. I don't. So I am not going to answer your question because I don't know.
সমস্যা নেই স্যার, লাইক জাস্ট একটু মাথায় আসছিল স্যার।
Sure, no problem. Good. মুনাম, তুমি কি কিছু বলতেছো? আচ্ছা। So what I want you to understand that how the math of this kind of questions could actually vary. Now here is the deal. This is what I want you to understand. This whole equation was derived under the concept that all the four velocities was going towards right, and we are going to write the equation, if we ever write the equation in our actual exam, in the exact same manner. There can be some other corollary versions of this which I'm going to show you after a while, but in any case, if an object is going in the opposite direction, do not change the shape of this equation. Don't. Simply replace the magnitude of that thing as a minus. So what I'm trying to mean, let's say if it so happens that you had two objects, one coming over here at 10 meter per second and the other one coming up over here as 15 meter per second. So what I'm going to do, if I consider towards right as my positive direction, and if I'm going to write this one as u1 equals to 10 meter per second positive velocity, and I have to write u2 equals to minus 15 meter per second. That's how I have to write this. So whenever I'm going to replace those numbers in my actual equation, u2 is going to be replaced as a negative number. But I will not, and you should not, write this equation as a minus sign right over here. Do not tamper with the sign of the equation. The generic expression of the equation should remain the same for the sake of simplicity and for the sake of easier working. M1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. That's the generic expression. But if you ever have to use vector quantities, which is pretty common, which are working in the opposite direction, simply place their number as negative, and it works perfectly fine. Yusuf, did you get your question answered?
Maybe not, sir.
What you asked me is that what if the two objects were moving in opposite direction? That's what you asked me. Before collision, or even if it can also happen that after the collision, the two objects are moving away from each other with some opposite direction of velocity. That can also happen, right? What then? In those cases, we are going to consider the opposite direction of velocity, magnitude, that value will be placed in the equation as minus. Because if I consider this vector to have a positive value, this vector cannot have a positive value as well, because these two vectors are in opposite direction. That's the whole point.
I mean, sir,
Bolo.
we'll just, switch the signs, right, sir?
বুঝি নাই
মানে স্যার শুধু সাইনটাই তো চেঞ্জ করে দেবো স্যার।
শুধু সাইনটা
Before
চেঞ্জ
collision.
করতে হবে, আর কিছু লাগবে না।
Okay, sir. Thank you, sir.
আচ্ছা, এখান থেকে আমাদের আরো কিছু ভ্যারিয়েশন আসতে পারে, সেই ভ্যারিয়েশন গুলো আমি একটু একটু করে আলাপ করতেছি। The first variation that we discussed from this equation is for the case of merge. Merge case means that if you have two objects which are going to collide into each other, let's say for this case I'm showing them to be of coming from opposite direction for whatever reason, doesn't matter. Let's say this is our u1, this is our u2. Now you might wonder, sir, আপনি minus u2 কেন লিখলেন না? Well, I'm representing them as u1 and u2. If I'm about to write their values, that's where I might write minus, maybe like that, which is perfectly okay. But for variable, I can use u1 and u2, no big deal. I don't have to write minus u2. I don't have to. Okay. So I'm not going to write values over here because I don't want to show you in terms of values. I want you to visualize this in terms of variables. So let's say we have two objects approaching each other from opposite directions, and after the collision, they actually get stuck with each other. So they actually become one. They get stuck or they merge with each other. And let's say that combined object, let's say this object has mass m1, this object has mass m2. After the collision, here we have the collision. So kaboom. And then the combined object of mass m1 plus m2 moves, let's say, towards this direction with a certain velocity. Now, what you kids need to understand, whenever we have a case of merge, these two objects m1 and m2 actually became one, which means you are not going to have two different velocities v1 and v2. Together, we can simply write they are going to have a single final velocity v. If you wonder, can v1 v2 লিখলে সমস্যা কি? What is the problem if we write v1 and v2? Well, be my guest, v1 equals to v2 as well. So there is no point to represent them as a different quantity, because as vector they're both moving in the same direction with the same magnitude. So might as well represent them as a single final velocity v. So the way this equation change in that scenario can be like this. Let's say m1 u1 plus m2 u2, and for the right hand side we just don't write two different final velocities. We give the mass within a bracket, m1 plus m2, there's a combined mass multiplied by the single object's combined objects final velocity. So that's one variation that we can have. That's for the merge case. The other scenario that can happen is what we call explosion. The scenario for explosion is that if you have an object that breaks down into multiple pieces. Now, if you wonder multiple pieces, what does that mean? Multiple pieces, in this case, we're going to consider only two pieces, but there can be more than two pieces as well for a two-dimensional or for a three-dimensional scenario. Very simple same thing. Let's try to understand one thing. You guys know grenades, right? I mean, not first hand, obviously, but you know what grenades are, right?
Yes, sir.
Grenades are a type of a ordnance or explosive ordnance. The way a grenade works, let's say this is a grenade. It has a fuse mechanism, and a typical grenade is perfectly round. But then again, we can have armor piercing grenades which can be a bit grooved. Why do we have those grooves? I'm not getting into that. So what happens is that inside there is a clip and there is a handle. So you pull out the clip, and even eventually when you let go of the handle, the fuse starts to burn. There is a spark which actually goes into this thing, and there is a certain fixed amount of explosive over here, which then undergoes explosion. That explosion produces a huge pressure, and because of the pressure, this whole outer cover breaks down into small pieces, and all of these pieces are shot into a three-dimensional spherical direction, in a spherical direction. So every people who are actually within that vicinity are shot with some sort of some shrapnels or some fractions of metal, which can be deadly if they go through some vital arteries, or if they fall on someone's eyes, or I mean that's basically the purpose of a grenade, to actually provide multiple big number of bullets, maybe small in size, but for a lot of people at the same time. So grenades are actually shot in rooms where there are a lot of people. So typically, but then again, in what is the game called, PUBG, grenades can be shot for fun as well. I mean, there are people who actually shoot grenades to their teammates to make friendly fire, and just revive them for no good reason.
Sir, you play PUBG, sir, then.
I used to. Anyway, let's not get there. But I know what happens in PUBG, and what happens in PUBG stays in PUBG. Let it be. So why am I telling you this? For the case of explosion, what you need to understand that whenever, if we have an object which is about to break down into two different objects, let's say we have an object which is stationary over here. For the time being, I'm considering it to be stationary. I'm going to apply a initial velocity after a while. Or I could actually start saying that this object has an initial velocity of u. Let's say for whatever reason, after a while, the object explodes into two pieces. Let's say it breaks down along this line and becomes object 1 and object 2. And so we have the explosion over here, kaboom. And then let's say object 1, sorry, object 1 should not be like that. No, not control A. What did I do? Control Z. So let's say this is our object 1. Let's say object 1 now moves in the opposite direction with, let's say, V1, and object 2 might move in the forward direction as V2. So that can happen. So this is the case that we got explosion. Whenever one single object breaks down into multiple pieces, there's the example that we call explosion, which is basically perfectly opposite of what happened here. This is the case for merge. Two objects became one. Here, one object became two. So in this scenario, we can rewrite the original equation like this: that m1 plus m2 multiplied by u, common initial velocity, should be equals to m1 v1 plus m2 v2. So that can also happen. এই ভ্যারিয়েশন গুলো বুঝা গেছে প্রমাণ কনসেপচুয়ালি?
লাস্টে কি বললেন আরেকবার বুঝতে পারবেন?
কোনখানে?
আমি ডিসকানেক্টেড হয়ে গেছিলাম 2 মিনিটের জন্য।
আচ্ছা, ক্লাসে বলছি যে এটা হচ্ছে আমাদের মার্জিং কেস where two objects after collision becomes one. So we have a common final velocity. So that's the equation. And the other case can be that we can have a scenario for explosion. The type of incidents which we define to be explosion are where one single object breaks down into multiple pieces. For the sake of simplicity, we're considering that this object is going to break into two pieces. Let's say piece 1 goes in this direction, piece 2 goes in this direction. So if we want to write the conservation of linear momentum equation for this case, we're simply going to have one single initial velocity, and the combined mass initially should be equal to m1 v1 plus m2 v2. That's how we can rewrite the equation. বুঝছো?
জি স্যার। স্যার ভেলোসিটি গুলো ডিফারেন্ট কেন? মানে v2 টা গ্রেটার v1 থেকে?
Well, I mean, I don't know which one is going to be big or small. What I'm trying to pose over here, that this one has a bigger mass and this one has a smaller mass. I'm trying to pose that because I do uneven pieces. So because I know that delta p1 equals to minus delta p2, so the product of mass and velocity should be equal. So if I draw a big chunk, naturally it should have a smaller velocity. Are you getting my point?
Yes sir.
Yeah. Hassan, go ahead.
স্যার মার্জিং হবে যখন অবজেক্ট দুইটার ভেলোসিটি সেম হবে, রাইট? এন্ড
Precisely. আচ্ছা,
স্যার
any further question? হ্যাঁ বলো, প্রজমা বলো।
আরো বেশি পিসেস থাকলে m3 v3 প্লাস m4 v4 এইভাবে কন্টিনিউ করবে।
হ্যাঁ,
For the
এভাবে
explosion
তুমি
one.
কন্টিনিউ করতে পারবে, এবং ওই জিনিসটাই হয়। আমি তোমাদেরকে এইমাত্র তোমাদেরকে ইয়ার এক্সাম্পল বলছি, কিসের এক্সাম্পল বলছি? এই যে গ্রেনেড এক্সাম্পল বললাম। গ্রেনেড হচ্ছে একটা 3 ডাইমেনশনাল অবজেক্ট which is going to shoot splinter in all 3 dimensional space, ঠিক আছে? x axis, y axis and also z axis. A very common simple 2 dimensional example হইতে পারে হচ্ছে একটা পুল টেবিল অথবা একটা ক্যারাম বোর্ড টেবিল। If you consider a carrom board table, let's say মনে করো মাঝখানে at the center you have all the গুটির ইংলিশ কি? গুটিবাজি গুটি না, মানে ফিজিক্যাল গুটির ইংলিশ কি?
স্যার ডাইস।
ডাইস, গুটি। Peg.
জি স্যার শিওর না স্যার
Sir, Google লেখেন what is Guti?
So let's go ahead with Guti. If I can't think of an English name, let's go with Guti. Okay. So let's say at the center you have the whole flower made up of all the Gutis of the carom board, and you hit it with a striker. So your striker comes in, and then the whole thing breaks up into a splatter. So that's the two-dimensional case where none of the things are actually expected to jump off the table. Do you get my point?
Yes,
Or
sir.
in a pool table, if you're taking a break shot to begin the match of the pool, then you are basically breaking the whole thing. So that's can be a two-dimensional case, and grenade can be a three-dimensional case. Or any firecracker can be a three-dimensional case, that is. Did I get your question answered?
Yes, sir.
And for all the three-dimensional cases or even two-dimensional cases, the vector equation will always hold true. For example, over here, try to understand this part, which is pretty interesting. For here, whenever we consider this to be as the formula for law of conservation of linear momentum, we are considering that the objects are moving in the same alignment. So all that it matters for us to do the math is to consider whether these velocities and these velocities should be represented as plus or minus. Because in a straight line direction, you can only have two directions, to the right or to the left, or to the up or down, or in any direction in the opposite direction. A straight line only can hold two opposite directions, right? That's why for the case of for the mathematical expression of conservation of linear momentum, you just have to consider plus or minus values. But whenever you go for a two-dimensional case or maybe a three-dimensional case, you need to work with components. I'm going to show you the case for two-dimensional scenario, which comes after a while. But before I go there, did you understand the example in its qualitative value?
স্যার এটা একটু আরেকবার বোঝাবেন স্যার
কোন পার্টটা?
মানে এটাই স্যার
মানে I mean, what is your question?
কোয়ান্টিটেটিভ ভ্যালু স্যার বললেন
কোয়ালিটেটিভ ভ্যালু, কোয়ান্টিটেটিভ না, কোয়ালিটেটিভলি যে আমাদেরকে শুধু প্লাস ও মাইনাস নিয়ে হ্যান্ডেল করতে হবে ফর দ্য টাইমিং, এই জিনিসটুকু হচ্ছে কিনা নিদিস
হ্যালো স্যার
মানে কোয়ালিটেটিভ জিনিসটা বোঝাচ্ছে যে মানে কনজারভেশন অফ মোমেন্টাম কনসেপ্টটা আমরা আপাতত শিখতেছি ফর দ্য সেক অফ সিম্পলিসিটি ফর দ্য লিনিয়ার কেস, but it is equally applicable for a two-dimensional scenario. It is equally applicable for a three-dimensional scenario. I don't know about four-dimensional scenario because I don't. I just don't. So, but what I'm trying to mean to you is that because we are considering this as a linear case for our mathematical purposes, all that we have to judge is whether the magnitude of these velocities should be placed as a plus quantity or minus quantity in the equation. That's all we have to judge for
Okay,
your
thank you.
requirement. It বলছি বুঝছো?
ইয়েস স্যার
আচ্ছা ঠিক আছে, আমি পিছে একটা ব্রেক নিব, আই এম a bit worn out. আমি 5 মিনিট পরে আসতেছি। আর আজকে তোমাদের ঈদের আগে লাস্ট ক্লাস, তো সো ক্লাস একটু লম্বা হতে পারে, মেবি 9:45 ish মতো হতে পারে। I'd appreciate if any of you can stay by, and if you have to leave for some other classes, you are welcome to do that. ওই পার্টটুকু পরে একটু দেখে নিও, কোনো কোশ্চেন থাকলে আমাকে মেসেঞ্জার জিজ্ঞেস করতে পারো, কোনো সমস্যা নেই। Taking the break.
স্যার
আচ্ছা নেভার মাইন্ড, পরে জিজ্ঞেস করলে আবার বলবো না।
স্যার একটা কোশ্চেন ছিল স্যার।
হ্যাঁ বলো।
স্যার এক্সপ্লোশনটা তো দুইটাই তো টু ডিমেনশনাল তাই না?
For once again, for the case of linear momentum, we are considering it to be one-dimensional. It can be two-dimensional. It can be three-dimensional as well.
এই সবগুলো হচ্ছে ওয়ান ডিমেনশনাল।
For our case of simplicity, yes, we are considering them to be all linear cases.
আচ্ছা স্যার বুঝছি স্যার।
So what we are going to see beyond this point is what happens for a two-dimensional scenario of a collision. So the two-dimensional case is actually quite simple. All that we have to do, first I'm outlining the process. We have to judge the same thing, conservation of linear momentum, for x-axis and y-axis individually. That's all there is. Nothing complicated, nothing too difficult. The figure is going to be a bit large. Just bear with me. Let's say here we have the object 1 of mass m1 going in this direction with a velocity of u1. Let's say this angle right here is θ1. Let's say here is our object 2. This is going in this direction with an initial velocity of object u2, producing an angle θ2 with the positive horizontal. Somewhere over here they do the collision. So I'm not going to draw the collision process because it is the reason why am I not drawing this, because it is possible the two objects might collide like this, but the forces might be this way. The two objects might collide like exactly vertically, but the forces might be vertical. The two objects might collide the other way. The two objects might collide like this as well, but the forces are going to be this way. The forces, because we are constantly distributed two-dimensional case, the two forces are going to be collinear. The two forces are going to be in the same line of action, but these two forces might exist in any alignment. So this variation is possible. That's why I'm not drawing any specific figure over here, just saying that they undergo a collision where the forces F1 and F2 exist for a duration of time t. So whole derivation process works for us. So this is before collision. After the collision, let's say object 1 goes away with a final velocity v1. Let's say this angle is alpha 1, and let's say object 2 goes away with in this direction. Let's say this angle is alpha 2. Now what I need you to understand, what I need all of you to understand, that this is a clockwise angle, this is an anti-clockwise angle, this is an anti-clockwise angle, and this is a clockwise angle, which means in terms of magnitude, if you consider this, what would be the magnitude of this angle, positive or negative?
স্যার কোনটা?
কোনটা স্যার?
θ1.
স্যার পজিটিভ স্যার।
No, clockwise angles are
স্যার নেগেটিভ স্যার।
নেগেটিভ স্যার।
all sin and cos. এরকম অ্যাঙ্গেল গুলো হচ্ছে পজিটিভ অ্যাঙ্গেল, এরকম গুলো হচ্ছে নেগেটিভ অ্যাঙ্গেল, ঠিক না?
আপনি আলফা 1 বলছেন, আলফা 1 বলছেন না?
না, let's say theta. I asked for theta 1. I'm sorry. If I theta 1 and alpha 2, these two will be negative angles, right?
Yes sir.
And these two will be positive angles. Now why am I specifying these things? Because this choice of value for these four angles, the type of values of these four angles, is going to automatically define the equation, because you need to understand that cos of minus theta ultimately becomes cos theta, whereas sine of minus theta automatically becomes minus sine theta. This is going to be extremely helpful for us. Let me show you how. I'm going to get rid of these circular stuffs because I want to write here. So let's say bad. So the way this equation is going to work out, if I write this equation for x-axis, m1 into u1 cos theta 1 plus m2 into u2 cos theta 2 should be equals to m1 into u1 sine alpha 1 plus m2, sorry কি করছি আমি ভুলে সাইন লিখে ফেলছি,
স্যার এক্স কি ছিল?
ভুল করতেছি বারবার। Converting all the velocities to their horizontal components with the cosine ratio. So the whole equation written for cosine format gives us the horizontal axis. And what is interesting for this scenario is that if you have a look over here, if you try to visualize all the individual components of all of these velocities, this is going to be a positive horizontal component. This is going to be a positive horizontal component. This is going to be a positive horizontal component. This is also going to be a positive horizontal component, which ultimately is obtained by using the cosine ratio, because cos minus theta gives you cos theta. Cos positive theta also gives you cos theta. So if you just place the angles over here, disregarding or not bothering about in which direction they are working, if you just place the angles properly, you're gonna have your math coming out just right. Let me write the equation for the y-axis, then I'm gonna start taking questions. So for the y-axis, the whole thing is gonna work out just exactly same, only the cosine ratios are simply gonna become sine ratios. So this is gonna how it looks like: m1 into u1 sine theta 1 plus m2 into u2 sine theta 2 should be equals to m1 into v1 sine alpha 1 plus m2 into v2 sine alpha 2. এই হচ্ছে y axis এর equation. Have a look at this whole figure and see if you have any question. I'll take questions now. বলো, anyone?
স্যার আমরা সবগুলো হরাইজন্টাল মোমেন্টাম হচ্ছে ইকুয়াল, মানে বিফোর কলিশন এন্ড আফটার কলিশন এক্স অ্যাক্সিসে,
Yes.
আর ওয়াই অ্যাক্সিসে বিফোর কলিশন আর আফটার কলিশন সেম। তো ওইভাবে আমরা এই দুইটা ইকুয়েশন ডিরাইভ করছি।
Precisely. The linear momentum for both the axes individually will be exactly same. So total momentum of the system in the horizontal direction before collision equals to total momentum of the system after collision in the horizontal direction. That's for the x-axis, and the same thing for the vertical direction for the y-axis. The reason I talked about this angle things is because if we can place this angles value correctly within the equation, automatically these plus and minuses would be converted to their required sign. For example, whenever you consider, if you place minus theta 1 over here and minus alpha 2 over here, you're still going to get a plus sign, because that's how cosine behaves. And that's basically what I showed you, that all the horizontal components are still working in the positive x direction, plus x direction. So they all should be positive components, and that's what you're going to get. Whereas if you place those same values in the sine ratio, the negative angles are going to give you downward direction. So this thing, when you are going to place the minus sine theta value for minus angle, this whole thing is going to become negative. And that's basically what's going to happen, because the velocity, initial vertical component of the u1 was working in the minus y-axis. Final velocity of the v2 was working in the minus y-axis. So these two things having negative angle, so something over here and over here should give us negative component. That should be automatically coming because of this property. That's what I'm trying to signify, that you don't have to bother to change the expression of the formula. As long as you place the values correctly, your math is going to work out perfectly every single time. Make sense?
স্যার, আর অ্যাঙ্গেলের যে ডিরেকশনটা, ওটা তো সবসময় যে এক্স অ্যাক্সিসের মতো যে ভেক্টরটা, ওইটার সাথে লাইন পর্যন্ত টেনে ওইদিকে ডিরেকশনটা হবে, তাই না?
Exactly. Or in other words, we can say that the angle should always be measured starting from the positive x-axis. If you remember that would be an easier version, I think. The angle should be always measured from the positive x-axis.
জি স্যার, গ্রেডিয়েন্টের মতো।
Precisely, গ্রেডিয়েন্টের মতো। Good. এই পর্যন্ত বুঝা গেছে সবার? I hope so. The next thing that we're going to see is এই জিনিসটা দেখো বোঝা যায় কিনা। In any collision, momentum will always be conserved. No questions asked. Total energy of the system will also be conserved. Total energy means the total amount of energy. Your initial amount of energy, final amount of energy, total combined total energy before collision should be also equal to total combined energy after collision, because energy is a conserved quantity by virtue. It's a conserved quantity. However, the kinetic energy of a collision, it might be conserved, it might not be conserved. Let me give you a simple example. Whenever two objects, especially for these cases, I mean, for the cases of merge and explosion, collisions always have different kinetic energy before and after. Let me give an example. Consider two objects which are going into each other. Consider a car accident. Two cars heading on into each other, crashing into each other, and maybe one is more massive than the other, becomes one, and eventually goes in one direction a little bit, and eventually the accident happened. Assuming there is no person involved, it's a test accident. In that process, we'll always have some deformation, because whenever you are considering that two objects are going to merge into one, there will be at least some amount of deformation. Even if there is no deformation, for the two objects to get stuck with each other, they have to be bonded by some force. Try to understand this concept. For the two objects to become one, they have to be bonded by some force. That force will be responsible to coerce the two objects to be together. And that's basically an expression of potential energy. Whenever within an object, multiple objects have some attraction within themselves, they have a stored potential energy, which in many cases we use as elastic potential energy, but it can be also come from van der Waals attraction force or polar molecules attraction force, so on and so forth. It can be also possible for metallic bonds, covalent bonds, you name it. So whenever you're going to have the case of a merge, some amount of initial kinetic energy that was available to the system initially. So what is the total kinetic energy before the collision? That is pretty simple, half m1 u1 square, and from here half m2 u2 square. For this is the total. If I sum these two up, this is the total amount of initial kinetic energy of the whole system considered scenario. But if a merge case happens, some of this kinetic energy will be definitely converted into potential energy. So total kinetic energy before collision and total kinetic energy of the whole thing after collision will not be equal. The total kinetic energy over here will be somewhat less, because some of the kinetic energy will be converted into potential energy of the system, because the two objects become merged together. So this is a case where kinetic energy is converting into something else. You have to understand that the energy is not being lost. Total energy is still remaining the same, but kinetic energy is becoming somewhat smaller because the objects got merged. This is the type of a collision that we can define to be inelastic collision. Have a look at the writing that I provided, that in any collision, momentum is always conserved. Total energy is also conserved. Kinetic energy before and after might be conserved, might not be conserved. If it is conserved, we call it elastic collision. If it is not conserved, we call it inelastic collision. Now, not conserved means before and after these two numbers not becoming equal. That's what we mean. এখন মার্জিং এর সিনারিওতে আমাদের আফটার কলিশন কাইনেটিক এনার্জি হবে বিফোর এর চেয়ে কম। সো ইন দিস কেস ke, sum of ke before should be somewhat bigger than sum of k after, because some kinetic energy would be spent to bond the two objects, which will be converted into potential energy. Vice versa, if you consider the case for an explosion essentially means you're going to have the objects pushed out from within. For example, for the case of a grenade, you have some potential energy, which is chemical energy somewhat, when it undergoes explosion, you have the whole thing exploding out. Now, this is not the same. I mean, to make sense of the explosion scenario, I gave you the examples for carrom board and also talked about the pool ball table, but that's not the scenario for explosion, because whenever for the case of pool ball table, actually, we also have some amount of energy loss, because whenever we hit the carrom board or pool ball table, there is no actually stored potential energy within the object, because none of those balls are actually spring loaded, or none of them actually breaks into pieces. Rather, what happens is that whenever the ball or the striker of the carrom board actually go ahead and hit your target, we have some conversion of sound energy. We can actually hear it, which means, I mean, and where did the sound energy come from? It actually came from the initial kinetic energy of the strike ball or the striker of the carrom board. So you are going to lose some energy, or even for the case of explosion, for the case of, for example, for a grenade, initially you have some potential energy over here. Whenever the explosion happened, all of these particles gained kinetic energy by the utilization of this potential energy because of the explosion, which basically means that in this scenario, total kinetic energy before should be somewhat less compared to the total kinetic energy after. This is a general discussion, but there can be exception of these cases. What I'm trying to tell you, in cases where one object divides into multiple or multiple objects become one, the collisions will always be inelastic, because kinetic energy will not be as before and after. There'll be some variation of kinetic energy. So kinetic energy will either be released, or kinetic energy might be absorbed and converted into some other form of energy. Abdullah, bolo.
স্যার তখনটা কোশ্চেন আর নাই স্যার, এক্সপ্লোশনের পার্টটা বুঝি নাই স্যার।
এক্সপ্লোশনের পার্টটা হচ্ছে, consider the case for a grenade. I mean, this is the or any firecracker. What happens for a firecracker or for a grenade? Inside we have some chemical energy stored by means of the blasting material, whatever the blast material is placed. Barud jetar bangla bole, English ki bole, gunpowder maybe. So whenever we burn the fuse, it undergoes a chemical reaction, and that releases the chemical energy, and that's what causes the whole thing to split into pieces, right?
Yes, sir.
So if, for the sake of simplicity, if you try to visualize that, let's say there is a grenade which is sitting on a table, someone pulled out the pin and he definitely walked away or ran away, and the grenade undergoes an explosion. So initially you had zero kinetic energy in the system, but when the explosion happens, you have a huge burst of kinetic energy for all the individual particles, right?
Yes, sir.
So where did that kinetic energy come from?
From the stored potential energy.
Exactly. So which essentially means that your final kinetic energy after the explosion will be definitely somewhat bigger compared to the initial kinetic energy of the system.
Yes, sir.
So this is also a scenario where kinetic energy before and after is not equal, or it is not conserved, in other words. Hence, we can always call these two types of scenarios to be cases of inelastic collision. This is the more common type of scenario. To be more, if I want to give you a more realistic life example, all the collisions that we experience in our regular life, they are practically all inelastic, because whenever any collision happens, objects undergo some type of deformation. Think about it. Even if you consider molecules colliding with molecules, there is always some amount of deformation within the bond. And whenever deformation is there, there is heat production. So why does the heat produce? One of the physical way that I can explain it to you is that layers of molecules, if you consider for a large enough object, layers of molecules rub against adjacent layers of molecules. So that produces some internal displacement of molecular structure within the object, and that produces some heating. So this is a very basic type of outcome for any type of collision. I mean, think about it. If you have two steel balls which are colliding into each other, what's going to happen? If you have a very high speed camera and try to observe this frame by frame, you're going to see they come into contact, and they squash onto each other's surface for a little while, and then they de-squash or expand out, and that's when they get out. So within this process of squashing and de-squashing, or compression, and then getting back to the original shape, or I can say decompression. I'm not going to say expansion because they don't actually expand. They decompress, so they get back to the original shape. Within this part, the object actually undergoes some amount of shape change, and that always produces some heat. Why am I sticking to this concept of heat so fiercely, or so adamantly? Because heat energy is the most common form of energy output for any real collisions, or which we pretty much experience in regular life. The other type of expression of energy we can have is sound. In many collisions, we can have sound produced, but there can be collisions where no sound is produced. For example, if you drop a rubber ball, I mean solid rubber ball, from a small height over a floor, you might not as well hear anything. The reason you don't hear anything, because rubber being such a squishy object, it produces a frequency that is below the threshold frequency of our ear. But if we had an elephant who can actually sense infrasonic sound, they might as well be able to hear it. So even if we don't perceive it, there is always some heat generation, and there's always some sound generation, typically because of the oscillation of the particles. And this energy output, I mean this sound energy and the heat energy that produces out of a collision, always comes from the initial kinetic energy of the whole colliding system. So that's why real collisions are always practically inelastic. That's why if you drop a ball onto a surface, we'll see that it slowly loses height, because after every single collision with the ground, it actually keeps on losing energy. You might also argue that it's actually losing energy with the air resistance as well. Totally agreeable. But then again, if we do the same experiment within a perfectly vacuum chamber, we would still end up with the same results. And in that case, the heat energy would still be produced. The ball might actually become hot, and the ground where it is hitting, that location might become hot. If there is no other way of heat transfer, there will always be conduction and radiation. If you vacuum up the whole environment, you might lose convection, but you cannot stop conduction and you cannot stop radiation. So those two forms of energy transfer can always happen. Heat transfer can always happen. Now, if you wonder, then, well, if that's the scenario for regular life, then what's the whole point of learning an elastic collision? Because elastic collisions is the simpler case where we can consider the kinetic energy is conserved, and inelastic collision is basically where we have to consider other type of energy conversion, and where we have to go dig deep under the molecular structure or the deformation of the objects, and so on and so forth. So inelastic collisions whole perspective is far more complicated compared to an elastic collision, because if you consider elastic collision, it's actually really simple. I mean, two objects are going to collide. They're not going to have any kinetic energy change, which means total kinetic energy before collision is equal to total kinetic energy after collision. So since there is no loss, we don't have to bother for sources of losses, which makes the whole scenario far too simpler. There can be one example for totally, actually not one. I could possibly tell you that there can be a lot of different examples, I think, for real life inelastic collision, elastic collision, where the total kinetic energy of the system remains same as the final kinetic energy of the system. One of the examples that I think you kids can actually make sense, which you have come to read across in your O-level syllabus, is the Rutherford's alpha particle scattering experiment. Anyone remember that Geiger-Martin experiment?
Yes,
sir.
Geiger-Martin experiment. So what happens in that experiment? We have a very thin gold foil, like super thin gold foil, and the scientists actually shot some helium nucleus, which is alpha particles, into that gold foil. And what they found out multiple things. Now, what I want you to assume, let's say, let me draw over here maybe. Let's say here we have a gold nucleus. So let's say this is a gold nucleus with all the protons and neutrons. So this is the gold nucleus. Gold nucleus number ভুলে গেছি। আচ্ছা বাংলা ইংলিশ লিখি gold nucleus. So it has some significant amount of positive charge because of all the protons. Let's say one alpha particle I'm showing this by a single dot, which is a charge of +2, is aiming directly towards the gold nucleus. Let's just consider that for the sake of simplicity. What's going to happen? There is going to be continuous electrostatic repulsion force. If the alpha particle does not have enough kinetic energy to begin with, because we are assuming it's not never going to penetrate, it's going to get close and going to slow down, going to get close and slow down, slow down, slow down, and eventually it might be able to reach to a pretty close point to the gold nucleus, at which point its momentary velocity will be 0. So this is the point where all the starting kinetic energy has perfectly converted into potential energy. And what do we call this potential energy? We call this electrostatic potential energy. The type of potential energy that is stored while working against an electrostatic force. We call it electrostatic potential energy. What's going to happen? Then the alpha particle is going to be once again pushed away from the gold nucleus, and is going to travel the whole distance on the same opposite direction. Because there are not too many gold nucleus, and the gold nucleus are really far apart from each other. So if you consider the practical force exists on a certain alpha particle is pretty much produced by one of the gold nuclei, or even if there are multiple, if it is possible that because there is no physical rubbing or no actual physical compression, because these two objects are actually not coming into contact, this kind of a collision can be considered to be an ideal example of elastic collision, because there is no actual contact. So there is no physical process for which they need to convert some of the kinetic energy into heat energy. So it's not a very regular life scenario, but it is one of those examples that I think you kids can actually perceive a little bit, because you are somewhat acquainted with this setup from your O-levels. Does this idea make sense?
Yes.
Yes, sir.
So you don't have to understand this whole thing to such a deep level, or don't bother for how much deep level you have to understand. All that is important for you to understand is these 3 bullets that I wrote over here, and it's very important that you do not forget the first 2 bullets. In all collisions, in any collision, momentum is always conserved. Total momentum before collision, total momentum after collision. Whether it's an elastic collision, whether it's an inelastic collision, you will always have the momentum conserved. Total energy will also be conserved. But kinetic energy might be conserved, kinetic energy might not be conserved. If it is conserved, we call it elastic collision. If it is not conserved, we call it inelastic collision. Now what I'm going to show you, what happens for elastic collision in terms of one last thing. All this 945. I just couldn't reach to the point that I wanted to reach it. Just one more thing. If I write up the equation, have a look over here. Half m1 u1 square plus half m2 u2 square equals to half m1 v1 square plus half m2 v2 square. I can get rid of all the halves. Then if I take the whole thing common over here, m1 into v1 square minus u1 square, and then equals to m2 into u2 squared minus v2 squared, which gives us m1 into v1 plus u1 into v1 minus u1 should be equals to m2 into u2 plus v2 multiplied by u2 minus v2. Now, one thing you have to understand, if the product of multiple things is 0, sorry, না এখানে তো কোনো কিছু 0 হয় না, কোনো কিছু 0 হইছে।
স্যার আপনি মনে একটা হাফ কাটতে ভুলে গেছেন স্যার।
Oh, thank you. আচ্ছা, আমি এটার ইকুয়েশন ডেভেলপমেন্টটা ভুলে গেছি, এটা আমার দেখতে হবে। There is a small equation of speed of approach and speed of separation equal হয়, ওটা আমি নেক্সট ক্লাসে দেখাবো না, আপাতত এটা বাদ দাও। হ্যাঁ, ক্লাস শেষ।
স্যার একটা কোশ্চেন স্যার।
হ্যাঁ বলো।
Thank you, sir.
For those who want to leave, you can take your leave. Yes, the class is officially over. Yeah, Isu, I'll take a question.
স্যার
Read করো,
স্যার
sir.
একটু ইলাস্টিক পটেনশিয়াল এনার্জি স্যার মানে ওই ডেফিনেশনটা কি বলেছিলেন স্যার এটা আরেকবার বলতে পারেন স্যার প্লিজ স্যার?
Elastic potential energy.
ইয়েস স্যার।
Whenever any object is deformed, the type of energy it stores within itself by virtue of its deformation is elastic potential energy.
থ্যাংক ইউ
Sir.
স্যার।
Sure.
Sir, in the alpha scattering experiment,
Bolo.
so you say the kinetic energy is transforming into potential energy.
Yes.
Then kinetic energy, how is the kinetic energy conserved? Like how will it stay the same?
Oh, acha. The idea is that if you want to consider a collision to be finished, you have to bring the whole setup to the same initial state. So what I'm trying to mean is that, let's say, I totally get your point. It's a beautiful question. Let's say this was the location of your alpha particle source. So I'm trying to draw a lead cube where you have some specimen which is producing alpha particles. Distance if it is smaller than 2 centimeters, or the whole, or maybe the whole chamber is evacuated so that alpha particles could travel the distance. Let's say let's say this is over here. I'm not drawing this over here. So let's say this is the point, this is the location where the alpha particle was actually released from the specimen. Do you get my point?
Yes, sir.
And mone koro, at this point, this was exactly, let's say, up to the gold nucleus. Let's say this was exactly 10 centimeter apart. I'm considering the whole experiment happening in vacuum, so 10 centimeter is okay.
Yes,
Figure, obviously figure not drawn to scale. Now, if it so happens that as the alpha particle will approach towards the gold nucleus head on, it will slow down definitely. Now, if you consider that your collision is starting when the alpha particle was released from the scenario, this is your starting condition. So what is your starting condition? Your starting condition is alpha particle was 10 centimeter away from the gold nucleus and approaching towards the gold nucleus. This is your starting condition. So for the sake of, I mean, I cannot say for the sake of, I mean, for obvious reasons, we have to consider the end of the collision for the exact same situation. I mean, when the alpha particle is going to reach over here and eventually come back, the moment the alpha particle will reach the exact same distance 10 centimeter away and is going to be moving away from the gold nucleus, just like that, that is when we can say the collision is over. Because we are considering, just a second, we're considering the approaching time towards the gold nucleus for a certain duration. So the getting away time, I mean, the t before and after the stop should be considered equal. Other than that, you are not going to have a complete collision. So for the same symmetric point of start and end, if you consider that, our kinetic energy will be conserved. So this is actually not happening for a very short period of time. It is definitely happening over a short period of time, but for the microscopic scale that we are judging, it is happening, the whole conversion is happening over a duration of time. But if you consider the start condition and the end condition to be exactly same, logically you should end up with the same kinetic energy as you started. That's why we can say that the kinetic energy is conserved. Good question. Yeah, I like it.
Yes, sir. Thank you, sir.
Sure. Anything else?
But sir, why is it same, sir? I mean, apart from that time, sir.
Oh, because you have the same amount of F into T. So you have the same amount of and you have the same amount of F into D. So the amount of kinetic energy conversion into potential energy conversion that you have over this distance, over the same amount of time, is the same amount of kinetic energy that you are going to get out of the potential energy over moving in the opposite direction. So in this process, K to P, K is 0, P maximum. In this process, P to K, here K is maximum and considering P is 0.
Okay, sir.
Okay, sir. Thank you. Goodbye.
Bye, sir.
তোমাদের সাথে
Sir,
এরপরে আবার পরের রোববার দেখা হবে ইনশাআল্লাহ। তোমরা এর মধ্যে কাইনেমেটিক্স এর P1 টা ট্রাই করতে পারো, প্রজেক্টাইল চ্যাপ্টার, তারপর গ্রাফের যে পার্টগুলো সেগুলো ট্রাই করতে পারো। মোমেন্টামের পার্টটা আগেই ট্রাই করো না, কারণ মোমেন্টামের পার্টটা ট্রাই করলে হয়তো অনেক জায়গায় হোঁচট খেতে পারো। I would say that try the P1 MCQ part within the Eid vacation. It's not, I mean, it's not a vacation if you have a huge homework, So I'm just going to ask you that try at your convenience. Just don't lose interest on physics. Do that much that doesn't repel you from physics. That's all I'm asking.
স্যার কোয়েশ্চেন স্যার অনেকগুলো স্যার 3-4টা কোয়েশ্চেন আছে স্যার
বলো।
স্যার পোটেনশিয়াল এনার্জি তো বললেন ইট ক্যান বি ইন দ্য ফর্ম অফ ইনস্ট্যান্টেনিয়াস ডাইপোল মানে ভ্যান ডার ওয়ালস আর ডাইপোল হইতে পারে স্যার তো এইগুলা কিভাবে পোটেনশিয়াল এনার্জি স্যার লাইক আমি যদি একটা মলিকিউলকে আরেকটা মানে একটা অপোজিট একটা চার্জড মলিকিউলকে একটা নিউট্রাল মলিকিউলের দিকে লাইক ছুঁড়ে মারি and then when it is going to the neutral molecule ওইটার তো বিভিন্ন ধরনের রিপালশন বা অ্যাট্রাকশন হবে স্যার ওইটার কারণে will it form any kinds of bond or how will that energy be stored in that molecule in the form of elastic ওটা কি আরো বন্ড ফর্ম করবে অন্য নেবারিং মলিকিউলের সাথে
It is possible that you might have some sort of bond. For example, one of the chemical process where we can say that there can be other type of bond is metallic bond. Whenever we make alloy, so whenever we make alloy, what do? We melt all the metals and then we get a composition that is uniform all over. That's what we call an alloy. So within the alloy, those new metal particles actually produce a metallic bond with the pre-existing metal atoms as well. So that can happen. And if chemical decomposition and recomposition does not happen, if two objects simply undergo a physical process of mixing, for example, let's say a basic sugar water solution, you don't have any chemical reaction there, simply the sugar crystal disassociates within the water because the OH of the, why does it dissociate once again? Because sugar crystals are what? C6H12O6. The
CH2ON formula.
Yeah, it's formula to CH2ON. Yeah, it dissolves because of the attraction of the water molecules on the sugar molecules. Because I think sugar molecules, does sugar molecules have charge because of the high electronegativity of oxygen molecules? I think so.
জি স্যার চার্জ হবে স্যার কারণ এই যে ইলেকট্রন ডিস্ট্রিবিউশন অ্যাসিমেট্রিক
Electron distribution asymmetric, and oxygen is highly electronegative, so it's going to pull more electron of the covalent bond towards itself, and the other hydrogen bond on the other side is going to have less because C6H12O6 এর মধ্যে C6H12O6 দাঁড়াও, there's 6 carbon on the side, then there are oxygen on the side by 1. It's a cyclic molecule, glucose. That overlaps. There are going to be some charge disproportionate charge distribution. So it's a physical process, but whenever the physical process happens, you do not have any essential chemical bond generated, but you do have some significant attraction that come into force between the dissolved sugar molecules and the water molecules, which didn't exist earlier before you made the solution, right?
Yes, sir.
So which means what? That attraction force actually pulled apart all the molecules from the sugar crystal and did the job of separating them out. Try to understand this thing. Visualize this thing. You have a sugar crystal. Try to visualize a single sugar crystal, which is where all the glucose molecules are in a single cube. Okay. If you want to separate each individual molecule within a volume of space of a glass of water, wouldn't you have to extract them out and pull them apart, overcoming the intermolecular forces?
Yes, sir.
So if you are working against some force, don't you have to do some physical work?
Yes, sir. ওই intermolecular forces গুলো break করার জন্য আমি hydrogen bonds form করতেছি.
Precise.
I am breaking them apart.
And that's also why typically the moment you make a sugar water solution, it usually becomes a bit cooler, because the amount of energy that it takes, actually it is absorbed as the thermal energy of the solution. Pretty soon it becomes same as the atmosphere, because atmosphere keeps on providing heat to cooler objects anyway. Any solution that you make usually makes the water, the solvent, slightly cooler, because the immediate energy requirement to disassociate the crystals is absorbed from the internal energy of the solvent.
জি স্যার। স্যার আরেকটা কোয়েশ্চেন স্যার। স্যার বলছিলেন যে কোনো ইনইলাস্টিক কলিশনের ভিতরে হিট জেনারেটেড হবে স্যার। Like sir, if I have two protons which are moving in a vacuum in a circular direction repelling each other, তাহলে কি স্যার
Hold on,
হিট
hold on. Circular
প্রোডাকশন
direction.
হবে?
Hold on. Circular direction means
স্যার মানে two protons moving like but like in a circular motion, like in respect to an object, like at a masser respect, like the electrons moving around the nucleus sir, মানে
electrons moving on the nucleus is possible. You have a positive nucleus, you have electrons, let's say first shell, helium going around. Yeah, okay, এখন বলো।
স্যার তো একটা ইলেকট্রন যদি স্যার মুভ করে লাইক দেন টু অরবিটালস ইন দ্য সেম অরবিটাল, তো দুইটা ইলেকট্রন থাকে, তো ইলেকট্রন দুইটা তো স্যার জীবনেও কোলাইড করবে না, দে হ্যাভ নেগেটিভ চার্জেস, সব দিন রিপেল করবে স্যার। So if they do not collide sir, how can they generate heat in a vacuum? If it's an inelastic collision, if there is like there's no collision at all that's happening though. Sir,
বলতেছি those two electrons will never collide with each other to produce any type of heat. But whenever you have a bunch of helium atoms confined within a chamber, they can generate heat, where different electrons from different atom will collide with each other. Those two electrons themselves will not produce heat, as far as I know, but I cannot say for this information for sure because I do not know how they behave quantumly. So as far as I know, the electrons that belong to a single atom, they will never collide or produce heat.
yes sir, so they're never gonna, it's never gonna happen, so this is buchi.
Okay, sure. Thank you very
Sir,
much.
this is Eid Mubarak sir, A level physics sir onek awesome sir, onek mojar sir.
Yeah, as long as you, I mean, you really put into the effort to visualize stuff, and I mean, once you start making sense of things, it starts falling like a Tetris box. Like you have a huge puzzle made, then you have all the vertical lines and your whole box is vanishing like that.
জি স্যার, স্যার আপনি স্যার অনেক ভালো পড়ান স্যার এখানে স্যার, আমাদের স্কুলে তো স্যার শুধু বলে দেয় এটা হয়, বাট দে ডোন্ট গো anywhere near those things, লাইক তখন অনেক আজব লাগে।
এ লেভেল তো হার্ড না, মজা।
আমি আমি
জি স্যার,
আমি
অনেক
আমি অনেক ভালো পড়াই এটা না, হোয়াট আই ট্রাই টু বি সেটা হচ্ছে আমি
তো শেষ।
আমি যতটুকু পারি আমি অতটুকু বলি যে আমি এইটুকু পারি বা এইটুকু আমি জানি, আর যেখানে আমি পাই না আমি বলে দিই যে আমি এটা জানি না। That's pretty much the only difference. The only reason a lot of teachers don't teach well because they, in many cases, I mean, I'm not going to say all of them, but there are some teachers who feel it uncomfortable to acknowledge that আমি একটা certain জিনিস জানি না বা আমি একটা certain জিনিস পারি না। They find it somewhat not so honorable, maybe. I don't know how to put that, and that's why they feel it uncomfortable to dig deeper within the topic of topic. But I am willing to dig deeper as far as my reach goes, and if it goes beyond that, I'm just gonna say it out loud that I don't know that far.
স্যার আপনি ছাড়া কেউ ট্রাই করেন না স্যার, আমাদের স্কুলেও কেউ দেয় না স্যার, আর স্যার এটা দেয়ার লাইক
তুমি কোন স্কুলে?
শিখবা
কোন স্কুলে পড়ো লেখাপড়া?
কোথায়?
মাস্টারমাইন্ড।
আচ্ছা ঠিক আছে, এটা পরে দেখা যাবে, সমস্যা